Good morning, students. Today we are going to discuss about motional EMF from Faraday's law and energy. Okay, so in last class we discussed motional EMF from Lorentz force, right? Motional EMF. So in that motional EMF, a rod moving in an magnetic field. In that rod, EMF is induced, right? So due to the induced EMF, current is produced. Okay, students. But here, motional EMF from Faraday's law. Okay. So therefore, see this. Let us consider one loop. So closed area, right? Okay. This is one closed area. This closed area in an uniform magnetic field. The magnetic field is perpendicular. See, this cross symbols represent the magnetic field, right? Okay, so this closed loop has four areas. Okay, and these four areas experience a force due to the motion of the due to the motion, right? So here the forces are this side experience a force F1, and this side experience a force F2, and this side F, this is total force, and this side F3. So these three sides experience a force because the object move from left side to right side. Okay, and the length here I am taking L. Okay, and distance moved, the loop is X. Okay, see this, when the loop is pulled with constant velocity to the right side, the area of the portion of the loop within the magnetic field will decrease. So due to this flux linked with the loop, because see this, the magnetic field is present, so therefore this loop is moved towards right side. Due to the motion, some flux changes. Due to the flux changes, an EMF is produced. Okay, the same concept of Lorentz force. When the conductor is moved in an uniform magnetic field with but constant velocity, definitely it experiences a what force. Due to the force, some EMF is induced. Due to the EMF, some current is created. So the current is induced in the material. Okay, the same way here, this is the loop moved towards the right side, that means from left side to right side in an uniform magnetic field with constant velocity. So due to this reason, yes, what is induced? EMF it is induced. Okay, students, right? Now yes, derivation is, see this, so please note it down. Motional EMF from Faraday's law and conservation of energy, or energy conservation, both are same, right? Okay, see, let X is the length of the loop within the magnetic field, then its area is L into X, length into breadth, right? So X is the length of the loop within the magnetic field. See, within the magnetic field, this is the S length. Okay, and then the area is equal length into breadth. No, that's why here L into X, right? Therefore the magnetic flux linked with the loop is, so what is the magnetic flux formula? Pi b which is equal to Ba cos theta, right? Yes, the same formula here. Pi b which is equal to integral A, that is whole loop. No, yes, entire loop, that's why I'm taking integral A, B into dA, which is equal to Ba cos theta. Here theta is equal to 0 degree, therefore cos 0 degree is equal to 1. Therefore the magnetic flux is pi b, which is equal to B into A. So here A is nothing but area, therefore the magnetic flux is pi b, which is equal to L into X. This is equation number 1. Okay, right? Okay, And yes, the next, due to the moment of the loop, I said no, the loop is moved from left side to right side. Due to the movement of the loop, EMF is induced. Yes, according to Faraday's second law, the EMF is equal to d pi by dt. That means rate of change of magnetic flux. Rate of change of magnetic flux, right? So in previous case we have flux. What is the flux? BLX. See this, what is the flux? BLX. That's why here E is equal to d divided by dt into BLX. So here L and B are constant. B is magnetic field and L is that length. Both are constant. Okay students, right? Okay, and then the EMF S E is equal to the BL come to this side, therefore dx by dt. Yes, this dx by dt is nothing but rate of change of displacement. Yes, the rate of change of displacement is denoted by v, that is velocity. Therefore this is equal to blv. Yes, so this dx by dt is nothing but v. This is equation number 2, right? Okay, from Lenz's law, induced current flows in clockwise direction, right? Please remember the Lenz's law. In Lenz's law, induced current always oppose. So therefore in which direction? Clockwise direction. Therefore the induced current is I, which is equal to E by R. That is V by R method. So E by R. So here what is E? Is BLV, no, from second equation. Therefore BLV divided by R. BLV divided by R. Okay, this is the which current? Is induced current. So therefore I is equal to BLV divided by R. That is equation number 3. Okay students, right? And come to the energy conservation. Yes, actually this is continuation. Yes, it is a 5-mark question. See this, energy conservation. The loop moving with constant velocity v is from left side to right side, now constant velocity v, that is equal to magnetic field. That is equal to magnetic field. So therefore mechanical work is done to move the loop. See this, the mechanical work is done to move the loop. Therefore the rate of is doing work. The rate of doing work is nothing but what? Power. Yes, therefore I am taking the power which is equal to F into V. F into V, right? So therefore the power is equal to F into V cos theta. So definitely some angle present, no? That's why F in magnitude FV cos theta. The magnitude of the power is FV cos theta. Okay students, due to the which one? Movement of loop with the constant velocity v. Okay, right? And here cos theta is equal to 0 degree, therefore the power F into V. Yes, therefore power F into V, that is equation number 4. So therefore in the loop the force F1, F2, F3 forces acting. Yes, but the general equation is force. Which force? Lorentz force. Which force? Lorentz force. What is the Lorentz force? F is equal to IL into B. F is equal to IL into B. So from that method F is equal to IL into B, right? So therefore I'm going to calculating the F1 force, F2 force, F3 force, right? See this, in F2, F3 both are is equal, that is equal in magnitude, equal in magnitude, right? Therefore I'm going to find out only F1, right? Therefore F1 force act on the left segment. Which segment? Left segment, because left segment in magnetic field. Therefore, according to the magnetic Lorentz force, F1 which is equal to IL into B, right? So here F1 is equal to IL B into sine theta. Yes, the magnitude is sine theta. Therefore, here sine theta 90 degree. Therefore, sine 90 is equal to 1. Therefore, the F1 force which is equal to ILB. ILB, right? This is equation number 5. Okay, students. And so here the total force which is equal to opposite to the F1 force, right? So in the diagram, the F force acting right side and the F1 force acting left side. Therefore, F is equal to minus of F1. This is equation number 5 I am taking. So the equation number 3 substituting in equation number 6. Okay. Therefore, F is equal to F1. Both are same. That is equal to which one? ILB. Right? Because high is also here. F value and F1 value both are same magnitude, acting in opposite direction only. Okay, both are same value but acting in opposite direction only. ILB. Therefore, I am substituting the values. Which value? I value in this equation. Therefore, IF is equal to, instead of I am substituting PLV divided by R into BL. Therefore, this is into BL, B square, L square, V divided by R. So therefore, F is equal to B square, L square, B divided by R. Right? This is equation number 7. The F value, total force on the right side is B square, L square, V divided by R. That is equation number 7. Okay, students? Right? Okay. Now, the equation number 7, substituting equation number 4 is, so which is number 4? See, this is the 4. Power which is equal to F into V. Therefore, the F value substituting in this equation, what is F value? B square L square V divided by R into V. Therefore, B square L square V square by R. So this is equation number 8. Okay, this is equation number 8. That is power is equal to V square L square V square by R. Right? So when induced current flows in the loop, Joule's heating will takes place. When the induced current flows in the loop, Joule's heating takes place. So Joule's heating is nothing but the loss of energy, right? Therefore, the power loss takes place. What is the power loss? Square value of the current and the resistance. Therefore, P is equal to I square R. Therefore, I value, I know that. What is I value? I value substituting. See this I value. Yes. See this BLV divided by R. Yes. So this I value substituting here, BLV divided by R the whole square into R. Therefore, see this B square L square V square divided by R square into R. So R square cancel. I can get the B square L square V square divided by R. The power loss. Right, in equation number 9. Yes, the power loss B square L square V square divided by R. So thus the mechanical work done in moving the loop appears as the thermal energy in the loop. Okay, the mechanical work done in moving the loop appears as thermal energy in the loop. So the 9th equation gives this conclusion. Okay, so this is the conservation of energy. Okay, students, right? Okay, students, see the video thoroughly and take notes. Okay, students, right? See the example problem 4.8. A conducting rod of length 0.5 meter falls freely from the top of a building of a height 7.2 meter at the place in Chennai where the horizontal component of Earth magnetic field is 40,378.7 nano Tesla, right? Okay, if the length of the rod is perpendicular to the earth horizontal magnetic field, find the EMF induced across the conductor. Induced across the conductor when the rod is about to touch the ground. When the rod is about to touch the ground, so here the G value is 10 meter per second square, yes, or ms power minus 2. Okay students, okay, yes, it is simple one. So in that question, data is given L is equal to 0.5 meter and height is equal to 7.2 meter and U is equal to initial velocity 0 meter per second and acceleration due to gravity is 10 ms power minus 2 and earth is horizontal magnetic field is 403 is 78.7 nano Tesla, right? So therefore, yes, to find the final velocity of the rod. So this is that equations of motion. From that equation, v square is equal to u square plus 2as. From that equation, please remember that equations of motion, yes, three equation will be there now. That's why here v square is equal to u square plus 2as. Instead of a is acceleration, here acceleration due to gravity, that's why g. Instead of s is displacement, but here displacement is h. Therefore v square is equal to u square plus 2sgs. So initial velocity is 0 plus 2 into g value is 10 and the height is 7.2 meter. Therefore v square is equal to 144. Therefore v is equal to square root of 144, 12 meter per second. 12 meter per second. Okay, velocity. Now come to the induced EMF when the rod is about to touch the ground. What is induced EMF? Induced EMF, please remember the formula. E is equal to BLV, no? Yes, the same one. Instead of B, here BH. What is BH value? Is 40378.7 into 10 power 9 because nano, that's why 10 power 9 into L value 0.5 and V value 12. Therefore, yes, 242.27 into 10 power minus 6 voltage. Therefore 242.27 is micro voltage. Micro means 10 power minus 6. Okay students, okay, so please near this you should write v square is equal to u square plus 2as from equations of motion. That's all. Okay, because height is the object travel from height, that's why we are taking that equations of motion. Okay, already studied in 11th standard. Okay students, right, next problem. A copper rod of length L rotates about one of its end with an angular velocity omega in an magnetic field B as shown in the figure. The plane of rotation is perpendicular to the field. So find the EMF induced between two ends of the rod. Right? Find the induced EMF between the two ends. Therefore, see the solution is given. So this area in a magnetic field, the total length of the rod is L and the displacement taken x, and after that dx is a small area. So in this area take the displacement due to the changes in displacement with respect to time, velocity will be takes place, but this rod moving in an angular velocity omega in anti-clockwise direction. So this area in an uniform magnetic field, right? So that's why see this solution given. Consider a small element of length dx at the distance x from the center of the circular described by the rod. as this element moves perpendicular to the magnetic field with the linear velocity v. So therefore velocity is equal to x into omega. Yes, and the EMF is developed in the element dx, right? Therefore, see the solution. The element moves perpendicular to the magnetic field with the linear velocity v is equal to x into omega, right? Therefore, okay, d is equal to, this is EMF formula BLV, no, is the same one here. d is equal to BV into dx. Yes, L is equal to dx here because the length. Therefore B into, I'm just substituting the V value. What is V value? X into omega. Therefore x into omega into dx. This is the EMF, right? Okay, the EMF developed across the two ends. Therefore I'm taking is integration. Therefore E is equal to integral dE. Therefore 0 to L, the minimum length is 0 and the maximum length is L. Therefore 0 to L bx omega into dx. Therefore b omega taking outside, integral 0 to L x into dx. So this x into dx, there is a formula is given. See this, x into dx equal to x square by 2. If I integrate x into dx, I can get x square by 2. Therefore this b omega s into x square by 2 in x square by 2 limits 0 to L. Therefore I am substituting the first upper limit and lower limit. Therefore instead of x I am substituting upper limit b omega into L square by 2 minus 0 square by 2. Therefore 0 square by 2 cancel, can get L square by 2. Therefore b omega L square by 2. If I am separate 1 by 2, the EMF is equal to 1 by 2 b omega L square. So this is the EMF. This is which EMF? Induced EMF. Okay, in the rod. Okay, students, right? Do you understand? Okay. Okay. Okay, students. Have any doubt? Yes, you have any doubt? No. Next is eddy current. Next is eddy current. Okay. Now, according to Faraday's law of electromagnetic induction, an EMF is induced. An EMF induced in a conductor when the magnetic flux passing through it changes. See, according to Faraday's law of electromagnetic induction, an EMF is induced in a conductor when the magnetic flux passing through it changes. Right? Okay. So electromagnetic induction and induced EMF takes place. Now, small introduction of eddy current. Eddy current are electric current induced in conductors when exposed to a changing magnetic field, and due to relative motion of field source and the conductor, or due to the variation of the field with time. So eddy current is our electric current induced in conductors. Okay, see the second point. This can cause a circulating flow of electrons. This can cause a circulating flow of electrons or current within the body of the conductor. Within the body of the conductor. Okay, and these circulating eddies of current have inductance and thus include magnetic field. That include magnetic field. Okay, Yes, see this eddy current. Yes, this is the magnet, has two poles. There is a small gap, and in this gap, this plate moving. Yes, that means oscillating. This part is oscillating from this side to this side. Okay, here constant magnetic field is present. Okay, and this is one metal plate. So in this metal plate, the magnetic flux changes due to the oscillation, right? Therefore, induced EMF created. Due to the induced EMF, current is produced. The currents are flow in circular loop. That's why it's called as eddy current. Which current? Eddy current. Okay, now see this circulating current called eddy current. Circulating current in the plate is eddy current, or induced in bulk pieces of metal moving through the magnetic field. So this is the metal moving in an uniform magnetic field. The eddy currents are in the opposite direction as the plate enter or leaves the field. If they enter field and is leave the field, which field? Magnetic field. Okay, now the eddy current are often undesirable because they represent a transformation of mechanical energy into thermal energy. Which energy? Mechanical energy into thermal energy. Okay, students, right? Okay, generation of eddy current. See this blue lines is the direction of which one? Eddy current. See this, when an electrically conductive material is placed in the coils, dynamic, magnetic field, electromagnetic, right, and induction will occurs, and eddy current will be induced in the material. So this is the simple way to create the eddy current. So this is the coil. The end of the coil is connected to the S1 battery, and this coil is attached to the small is metallic plate. That's why see this, when an electrically conductive material is placed in the coil's dynamic magnetic field and electromagnetic induction will occurs, and eddy current will be induced in the material. So this is the material. Then in the eddy current flows like this, closed S loop. Okay, right. And eddy current or Foucault current, both are same. Eddy current, another name is Foucault current. Is in brief explanation, please listen. Eddy currents are loops of electrical current induced within conductors by changing magnetic field in the conductor according to Faraday's law of induction. It's induction, Faraday's laws of induction. And also circulating currents are induced in bulk piece of metal moving through the magnetic field, as the shown in the figure like this at the left hand. As the plate enters the field, the changing magnetic flux induces an EMF in the plate. Okay, and which in turn cause the free electrons in the plate to move, producing a swirling eddy currents. Yes, swirling eddy currents. So according to Lenz's law, the direction of the eddy current is such that they create magnetic fields that oppose the change that cause the current. Okay, so what is another name of eddy current? Foucault current. Okay, so according to Lenz's law, flows in opposite direction. Okay, students, right. See this. So this is that metal, and this is the coil connected to AC. So when the coil is attached to the metal, the flow of alternative current, electromagnetic induction takes place. Due to the electromagnetic induction, eddy current produced the eddy current induced in the metal. That's why eddy current is swirling current set up in the conductor is a response to change the magnetic field. Due to that, eddy current will be produced. The eddy current flows like this. Okay, okay students, right. And this is the book diagram. Yes, the metal plate is attached to the rod. The rod is fitted with the one fixed bar. Yes, and same time we are taking the magnet. The magnet is surrounded by the coil, and the coil is connected to the battery. Yes, when the switch is open, there is no current, but the switch is closed, some current flow to this magnetic field, right? Due to this current flow, the magnetic flux present here. Due to the motion of this metal plate, magnetic flux changes. Okay, magnetic flux continuously changes. Due to this, in the metal, induced EMF created. Due to the induced EMF, some current flows in a circular loop. So that current is nothing but eddy current. Which current? Eddy current. Okay, if you use this type of area, there is no eddy current present in this one, because if that using the closed plate only induce a current created, but like this type of material, it does not create any eddy current because there is a gap. So in that gap, what is present? Magnetic field is present, therefore there is no changes in magnetic flux. Okay students, that's why A, B, C, 3 diagrams. Okay students, right? Okay, drawbacks of eddy current. Drawbacks: when eddy currents flows in the current conductor, a large amount of energy is dissipated in the form of heat. When the eddy current flows in the conductor, the large amount of energy is dissipated in the form of heat. This energy loss due to the flow of eddy current is inevitable, but it can be reduced to a greater extent with suitable measures. Therefore, the design of transformer core and the electric motor armature is crucial in order to minimize the eddy current loss. To reduce these losses, the core of transformer is made up of thin laminous insulator. Please underline thin laminated insulated from one another. So while for electric motor, the winding is made up of a group of wires insulating from one another. Yes, with the help of the insulation only we can minimize the heat loss in transformers. So this is the main drawbacks of eddy current. Okay, main drawback of eddy current. Okay students, right, and see this is the laminated core. This is the single lamination, and this is the laminated core. Around 50 core is present. Insulated laminates of core of transformer, and this is the coil, insulated winding of electric motor. See, this is that copper coil. This is the whole setup is winding. So this is the major part of the transformer. Nice, sorry, electric motor. Okay, so this is called as rotor. Entire setup is rotor, and this is the coil is connected to this end. Okay, this coil moving in an uniform magnetic field only, what will produce? Electric current is produced. Okay students, right. And application of eddy current. Though the protection of eddy current is undesirable in some cases, it is useful in some other cases, right? Therefore, a few of them are the applications of eddy current. The eddy current are used in induction stove and eddy current brake, that is used in braking system, and eddy current testing and used in testing purpose, and electromagnetic damping. Yes, so eddy current used in electromagnetic damping. Yes, So these are the four areas. Okay, major four areas of eddy current. Okay students, right? And see the first one, induction stove. See this cooking zone, and this is coil. Is under that the coil is placed like this. Okay, and this is the cooking pan. High frequency alternating current. That means here the coil is connected to the alternative current with the small circuit. No, therefore when the current flow to the circle coil, it will produce was eddy current produced due to that is cooking process takes place. Okay, induction stove. Okay, you will see that backside of the induction stove you will see the circulating coil or circular coil. Okay, okay students, right? Now eddy current brakes. So this eddy current brakes in uh, used in train braking system. So these are that small 1 2 3, these are the is electromagnetic materials. See, this eddy current braking system is generally used in high speed trains and roller coasters, right? See, like this. So opposite is magnet and the bottom of the metal sheet. Due to this one magnetic present, when when we are apply the current, due to the electromagnetic induction here in that plate, eddy current is produced. Okay, see that strong electromagnets are fixed just above the rails. See, this is this electromagnet. See that these are the electromagnet. Okay, and top to stop the train, electromagnets are switched on. The magnetic field of these magnets induced ND currents in the rail which oppose or resist the movement of the train. Yes, this is the eddy current linear braking system used in bullet trains. Students, right? See, this is that view. So this is that plate, braking plate, and this is nothing but electromagnet. This is the small electromagnet. So this is that braking plate. So in that plate only what is produced, so what is created, eddy current is created. Okay, actually this is the braking pad. Okay, in trains. Okay students, right? Okay, next is eddy current testing. It is one of the simple non-destructive testing methods to find defect like surface cracks, air bubbles present in a specimen, right? A coil of insulated wire is given an alternating electric current so that it is produced an alternating magnetic field, right? And when this coil is brought near the test surface, the eddy current is induced in the test surface. So therefore the pressure of defect causes the change in phase and amplitude of eddy current that can be detected by some other means. So in this way the or defect present in the specimen, right, for to find out that any cracks, any bubbles, for testing purpose. This type of testing methods used in quality checking is which one, quality is checking side, that is used in quality control side. Okay students, right? And see, this is the testing. So this is the is coil attached to the current, coil magnetic field, and eddy current is present in that material in a closed loop. Eddy current, magnetic field. So due to that current around this coil, magnetic field present like this. due to the magnetic field. Here what is present? Eddy current are produced in the closed loop in the material. Okay students, so based on this one, to test the quality of the material, that means any cracks. Okay, and last one is electromagnetic damping. The armature of the galvanometer coil is wound on a soft iron cylinder, right? Yes, if you go to the galvanometer, the needle is attached to the coil and with a small magnet. Okay, that's why soft iron cylinder. See this? So this is that frame. There's the coil. Inside the coil, one magnetic uh, one plate is attached, and that top of the needle attached to the needle is an opposite side magnet is present, north pole and the south pole. So that armature is deflected when the current flows, right? The relative motion between the soft iron cylinder and the radial magnetic field induces eddy current in the cylinder. Therefore, the damping force due to the flow of eddy current brings the armature to rest immediately, and then the galvanometer shows a steady deflection. So this is called electromagnetic damping. Okay, due to the eddy current only it comes to the rest, and it shows that constant position. Okay, in galvanometer. Okay students, so because the galvanometer to measure the flow of current in a circuit, right? So when the current flows to the coil, what is produced? Deflection produced, no? So but in that that soft iron core is to produce the deflection. Okay, so based on the damping, yes, process. Okay students, so inside that we called as damping, electromagnetic damping. Okay, in galvanometers. Okay students, so these are the applications of which one? Eddy current. So eddy current used in induction stove and braking system and testing purpose, and electromagnetic damping. Okay students, okay, right. Thank you students. Today class is over. We'll see you on next video. Okay. Thank you.